Hey everybody. Okay, first of all, here's my picture of the teacher. And yes, I typed in teacher working at home and that's what came up. So I kind of like this guy. I might stick with him for a little while. Slide 40. Okay, they give you a competing precipitation. Lead and silver, we're going to add sodium chloride. So the common ion is chloride. And they want to know what is the silver concentration when the lead chloride begins to precipitate. Now, this is a little different than the other problem because in the other problem, they wanted you to determine that the silver chloride would precipitate out first because it has the lower KSP, and that's true. But we're going to do a Le Chatelier shift to the left on that. So silver chloride produces silver ions plus chloride. And so as we continue to add chloride ions, this is going to shift this to the left, and we're going to wind up with a much lower concentration of silver once the lead chloride starts to precipitate. And that's the key. They said once the lead chloride starts to precipitate. So we can use the lead system to figure out what the chloride concentration is at that point. And then once we know the chloride concentration, then we can go back and figure out the silver concentration. So lead chloride produces lead plus 2 moles of chloride, and the KSP for this is lead times chloride squared, and we can solve for the chloride concentration on that. So if I define the lead concentration to be X, then the chloride concentration would be 2X. But we pretty much know the lead concentration. It is just about to precipitate. So at the moment that it starts to precipitate, it is 0.10 molar lead, because lead nitrate, nitrate's a spectator, so this is completely soluble. So I can substitute in that value for the lead, and I can solve for the chloride. So we're going to get KSP is equal to 0.10 molar times 2x quantity squared. And let's rearrange this. So we get 4x squared is equal to KSP divided by 0.10. And x is going to be the square root of KSP divided by 0.10 divided by 4. So we'll substitute in 1.7 times 10 to the minus 5 for the KSP. And let's see what we get for X. Ah! I got hit with a calculator. I'm injured. Divide that by 4, and we take the square root of that nonsense, and I get 0.65 or 6.5 times 10 to the minus 3. So the chloride concentration is going to be equal to 2x. So we get 0.013 molar. All right, so now that I know that, I can go back to my silver chloride concentration, or my silver chloride system rather, and I can say, all right, KSP for silver chloride is equal to the silver times the chloride. And let me see, what's the KSP? 1.8 times 10 to the minus 10. And we'll divide that by the chloride concentration at that point, and we get a silver concentration of Negative something. Okay, I must hit the wrong button. 1.8 exponential negative 10 divided by 0.013. Okay, this is more reasonable. 1.4 times 10 to the minus 8 molar. Okay, and let's see if that matches. Yay, it matches, hooray. So again, what they're dictating there is they're saying, look, yeah, we can figure out that there's going to be some silver there, not much. 1.4 times 10 to the minus 8 molar is a very tiny concentration, and it's dictated by the fact that we have such a large amount of chloride in there. And again, it's at the moment that the lead starts to precipitate, of which the lead was 0.10 molar lead nitrate. So we use the lead to figure out the chloride concentration, and then once we know the chloride concentration, we come back to our silver system and calculate the silver ion. All right, the second one was a little more difficult, slide 41. What's the mass of silver chloride? And we have 1 liter of 1 molar ammonia. Now, as soon as I see that, I'm thinking ligand complex, because I know that ammonia has an unshared electron pair, and the silver chloride is a transition metal, and they're giving me KF and KSP. So the reaction is we're going to dissolve the silver chloride by adding a ligand, and I know it's 2 moles of ammonia for 2 reasons. One, the charge on silver is +1, and usually the amount of ligands is double what the charge number is. So if it was +2, there'd be 4 ligands. If it was +3, there'd be 6 ligands. Second, if you look at the product for KF, there's 2 moles of NH3 in the formula right there for diamine silver plus. So this is going to produce diamine silver plus the chloride ion. And so this is just a KEQ problem after that. We can say KEQ for this reaction is equal to, it said the formula was KSP times KF, and that's also equal to the complex, right, products over reactants, times chloride over ammonia squared. And the issue with this is that when we do KSP times KF, it comes out to be a number that's really close to our original concentration. So we're going to have to use quadratic here. So 1.8 times 10 to the minus 10 times 1.6 times 10 to the 7th is equal to KEQ. So KEQ for this reaction is 1.8 exponential negative 10 times 1.6 exponential 7, syntax error because it's like that today, times 1.6 exponential 7. I get 2.9 times 10 to the minus 3. And that's going to be really close to our 5% issue. So when I set up my equilibria chart, I'm going to use quadratic. So I get my chart. Initial, change, equilibria. We have the silver chloride plus 2 moles of ammonia produces the diamine complex plus chloride, and make my little columns. And I do not care about the silver chloride because it's a solid. So this is going to start out as ammonia as 1 molar, and then it's going to change by 2x. My products start out as 0, and each of them goes up by x. So this winds up being 1 minus 2x. This is x. This is x. Now I can substitute into KEQ, and I get x squared over 1 minus 2x is equal to 2.9 times 10 to the minus 3. And at this point, I would solve that, or set it equal to 0, and then use quadratic. So I can write at this point, I can write by quadratic. Hey. Quadratic. quadratic? No, there's a freaking T in there. Formula. All right, concentration of X is equal to 0.048 molar, and that is also equal to the concentration of the chloride. Now, why is that important? Because in terms of solubility, for every 1 mole of silver chloride that actually dissolves, it produces 1 mole of silver. But we have a large chloride concentration which dominates the equilibria. So I'm going to go back to KSP here. And I'm going to say, all right, the KSP of the silver system is equal to silver times chloride. And at this point, we have a huge Le Chatelier shift to the left because this chloride concentration is large. But I know that the solubility of silver chloride is going to be equal to the silver concentration. So I'm going to solve for the silver concentration. And I get that to be equal to KSP divided by chloride. 1.8 times 10 to the minus 10 on the KSP. 0.048 on the chloride. And I get a silver concentration of 1.8 exponential negative 10 divided by 0.048. 3.7 times 10 to the minus 9. 3.8 if you're using the old rounding rule. Molar. And we're dealing with 1 liter of solution, which is convenient because now I can just convert that to grams. So we have 1 liter of solution, and we're going to multiply that by 3.7 times 10 to the minus 9 moles of silver per 1 liter of silver. And I know that 1 mole of silver is equal to 1 mole of silver chloride that dissolves. And 1 mole of silver chloride has a mass of a million, a billion, a trillion. Let's go back to our periodic table for a moment. Hey. There we go. All right, silver is 107.87. Plus chloride, 35.453. I get 143.323. Grams of silver chloride. All right, so let's multiply that out. So we're going to take that and multiply it by 3.7 exponential negative 9. And I get a totally messed up answer, of course. Oh, I'm sorry. Here's the problem. The amount of chloride that dissolves in this system is actually equal to the silver, which is equal to the silver chloride. That's the mistake here. Yeah, it's not a Le Chatelier shift because we're no longer dealing with this system. What we're actually dealing with is a ligand complex, which means that we're forcing the ligand complex to cause the silver chloride to break up into silver complex and chloride. So how much of this dissolves is actually equal to the chloride because we're no longer dealing with silver ions by themselves. We're creating the silver diamine complex. I'm sorry, my bad. So all of this part right here we can get rid of, and we already calculated the chloride, which was 0.048. So let's try that instead. My bad. All right, so 1 liter of solution. I know that in 1 liter of this solution, 0.048 moles of chloride are produced. And for every 1 mole of chloride, that means that 1 mole of silver chloride dissolved. And I know that for every 1 mole of silver chloride, we get 143.323 grams of silver chloride. See if it works out this time. 0.048 times 143.323, and I get 6.9. Yay, I can be taught. 6.9 grams of silver chloride. Sorry for the mistake. My mind is on 5 different things. I apologize, but I hope you understand. I'll go back through it now real quick. Again, we're not dealing with the silver chloride system per se. What we're doing is we're using a ligand to create a formation reaction. So the ligand is going to cause the silver chloride to break up by producing the silver diamine complex and chloride. The formula for that, for the KEQ, is KSP times KF, which they gave you. The KEQ we calculated, and then we set up our equilibria chart. We used quadratic formula to solve for chloride, and it turns out that the chloride concentration is equal to the amount of silver chloride that dissolves. So let's clean this up a little bit. Let's get rid of this evidence of incompetence. And we're going to say that the solubility of the silver chloride, for every 1 mole of silver chloride that dissolves, we get 1 mole of chloride ions. Let's get rid of this for shame. And so we can just do this calculation here once we know the chloride concentration. Thank you.